So for today, I wanted to introduce two very important limits over here. And what we're going to try to do is we're going to actually approximate these limits, because it's quite difficult to actually take the limit using direct substitution, as you'll come to find. We're going to see how this limit over here in particular, the limit as n approaches infinity of 1 plus 1 over n, all of that to the nth power, will eventually converge to a very special number, which is in fact e, which I've written out, of course, this isn't accurate. We know that e is not a terminating decimal, it's an irrational number. However, we can see that as n approaches infinity, our limit over here will get arbitrarily close to e. And so let's go ahead and do that. Let's just take different values of n. So let's just take n equals 10 to the third, which is already a very large number. That's like 1,000, right? So then f of n, I call this function over here f of n because I didn't really want to rewrite this expression in the limit multiple times. And so if we put 10 to the third into our expression for f of n, then on the calculator you will get approximately 2.71692932. And of course, this isn't a terminating decimal, this is just an approximation. And you can already see, we're accurate to 3 decimal places, right? We have 2.71 for e, here we have 2.71, and then, of course, it starts losing its accuracy after the second decimal place. And so then, if we take a slightly larger number, or actually not a slightly, a significantly larger number, if we take 10 to the fifth, then f of n will give us this number over here, which is even closer to e because we have now 2.718, and then we have the 2 over here, and then it starts losing its accuracy after the fourth decimal point. If you want to compare it actually to to e right over here, where we reach the 2 and then we would have an 8, here we have a 6, 8 after the 2. But I mean, if you approximate this as 2, 7, then it is extremely close to e as well, right? And then if we take 10 to the 7th, n equals 10 to the 7th, an even larger number, and we input that into f of n, we get this number right over here, which is now accurate to even more decimal places, right? Because if we look, it's going to be accurate to what? 1, 2, 3, 4, 5. In fact, it's going to be accurate to 6 decimal places before it starts losing its accuracy towards the end over here. And then we can take an even larger number. And I could have, I tried putting in 10 to the 100th power, but then, the calculator just started approximating 1 plus 1 over 10 to the 100th to be equal to 1. And so that wouldn't really serve us much of a purpose. But 10 to the 9th, you can pick n equals 10 to the 9th, for example, input that into f of n, and we will get this number that is extremely close to e. We get 2.718288182, and then we get a 7 at the end, which is almost identical to e's approximation, except with e we end with an 8. And so the point is that this limit right over here, as n approaches infinity, is in fact equal to e. And this is, I'm assuming you're at least slightly familiar with e from your Algebra 2 or your pre-calculus classes, because e is a very, very important number that we're going to come to find serves us many different purposes throughout calculus. And so I tried to kind of give you a little sketch of the graph of f of n. And essentially, so this is the point, I'm pretty sure this was the point 0, 1, where we have a point discontinuity, and then we have an asymptote right over here. I don't know why I didn't draw out the asymptote. It's actually supposed to be on the x-axis, but that's fine. Or sorry, yeah, on the y-axis. I don't know why I said x-axis. And we know that, by definition, taking the limit as n approaches infinity gives us the different vertical asymptotes, the horizontal asymptotes of the function. If we take the limit as n approaches plus or minus infinity, we can see kind of what happens to the function as n gets infinitely large in either direction, and that gives us the different asymptotes of the graph, if any, of course. And so right over here, it turns out, even if you graph this, you can actually take a look at it graphically. It turns out that this asymptote is given by y equals e. So we know that this function is going to asymptote to e as n approaches infinity. And so essentially, we have different ways of actually getting, or I guess you could say not necessarily deriving, but of producing e. We can take this limit over here. We can even consider it geometrically through the graph, and we'll look at the asymptote of the graph. And one final thing before we get going, I just wanted to give you the definition of e to the x. There should be an n right over there. And that's the limit as n approaches infinity of essentially the same exact thing, except with an x above the n in the expression, I suppose you could say. And so this thing right over here is n approaches infinity. This thing will get arbitrarily close to the e to the x graph. And so these are all very important applications of limits, in the sense that we're going to need e and e to the x very much throughout calculus. And so it's good to kind of have an understanding of where these different numbers and functions come from.